All right, good morning, everybody. Welcome to lecture this morning. Hope you all had a nice weekend and didn't watch too much basketball. I know I did. Just a quick reminder that homework 6 is due on Friday. That's coming up kind of quick, although if you've taken a look at that, it should be a little bit more straightforward than the previous homework assignment. I don't think that'll take you too long. It's just calculating a bunch of confidence intervals, kind of doing that a number of times. So I want to finish up. We're going to do one more example from Chapter 7. I want to do this before we moved on. We'll start Chapter 8 then in short order. I have your exams almost graded, and we'll have those back to you on Wednesday. Grades should be up maybe later today or tomorrow morning at the latest. So stay tuned for that. Other questions or comments? We all good? They're looking. I will not make any comments on that at this point. I'm not the whole way through them yet, though. So, and I have not totaled any of the grades. It's hard to know before you actually total up the scores. Okay, so we're going to finish up this one more example that's actually not written in your notes for Chapter 7. But before we do that, I wanted to just kind of review what we're doing and kind of your general procedures for doing these confidence intervals. So sort of your first step, and some of the questions in the homework sort of ask you to explicitly work through or think about some of these conditions. But before you actually go about calculating a confidence interval, you want to make sure that it's sort of okay to use the formula. And that involves checking kind of two conditions. One of them sort of is always the same, and the second one is sort of a large enough condition, sort of what we'll call it later anyway. But so we do always sort of need to make sure that we have a random sample. Sort of independent observations is what we need for the central limit theorem to kick in and for the sample mean to have a normal distribution, all that stuff. So kind of just think about that a little bit. Again, it might not always be stated. If it's not stated, think about where the information came from. Is it something that should be a representative sample, hopefully, or at least not biased? And then for the test for the proportion for the confidence interval for means, you want to check one of these things. So, am I told anything about the population distribution? Is it normal, or am I not told anything? And then thinking about if you know what sigma squared is. So if I know what the population variance is, that sort of changes which formula I use. In the most general setting, if I don't know the population distribution, so I'm not told anything about it being normal or anything like that, and you also don't know what sigma squared is, then we can use the t confidence interval as long as your sample size is large enough, or bigger than or equal to 30 is kind of the magic number we're using here for this class. Okay, well, all this is a review, but then just to remind you that the formulas here are as follows. Each one of these guys is our estimate. General form here, estimate plus or minus the margin of error, which I think we called E as our notation there. That's kind of what a confidence interval will be in general. We're going to take our estimate of whatever we're trying to estimate and add and subtract something based on what distribution that thing has. So when we're estimating a population mean, we're going to use the sample mean x bar, and then we're going to add and subtract margin of error, which is critical value times its standard error there. And then if we're talking about proportions, just remember we also introduced a way to give a confidence interval for a proportion. So if I'm talking about some probability of success or some proportion of something, I can use the sample proportion and calculate it as follows there. P hat, this is my sample proportion. Which is the number of successes divided by n. So whatever it is we're talking about, we'll generically call that a success, the number of successes that I have out of the total sample size. And again, here I do need to make sure to check that I have a random sample. But if you notice in that definition there, I also want to make sure sort of here's my large enough condition kind of like checking if the sample size is at least 30. But in this, for proportions, the formula is slightly different. Just want to make sure that n times p hat is at least 10, as well as n times 1 minus p hat bigger than 10. Okay, so just to remind you, what are these z sub alpha over 2 and t sub alpha over 2, comma n minus 1? Remember, those are critical values. So we're calculating those based on which confidence interval I have. So do I want a 90% confidence interval? Do I want a 95%, 99%? Anything there, really. And just remember, if I have for a z sub alpha over 2, that's the number such that, that's the number down here on the axis, such that the probability of being bigger than that is alpha over 2. And same for the t distribution there. It just depends on the degrees of freedom, which is n minus 1. So just remember, those are critical values. That's our terminology for them, and this is what they mean. We just want to find the number such that there's alpha over 2 probability above that number. Okay, so that's my quick recap. Any questions, comments? This all feeling okay? Okay. Well, like I said, I wanted to do one more example, and I wanted to take this one a little more from start to finish, to kind of just sort of reiterate where this information is coming from. Start with some actual data and use that data to calculate a confidence interval here. So this one's out of your textbook. The example here, we're going to talk about asbestos. And so an article in the Environmental Research Journal reports results on a study where they looked at a sample of construction workers who'd been exposed to asbestos over a long period. And some of the data that was reported in this study were these numbers. So this is the pulmonary compliance for each of 16 subjects after 8 months of being exposed to asbestos. So, and that's in units, centimeters cubed per centimeter of, H2O. Okay, and so what I want to do here is estimate sort of the true average pulmonary compliance of workers who are exposed to asbestos. And here's my data. Okay, so normally in a problem we'll tell you here's the sample mean, here's the standard deviation. Kind of wanted to step through actually showing you how to do this. Okay, so again, the question here is I want to estimate the true average pulmonary compliance. And so again, thinking about estimation, in Chapter 6 we talked about how to find a point estimate for our parameter of interest. And then in Chapter 7 we talked about we can generalize that to give a slightly better answer if we give a confidence interval. So I want to estimate something about the population. So I want to estimate mu here, which is the true average pulmonary compliance of workers exposed to asbestos. So that's what I'm trying to estimate. Okay, so again, our first step for these confidence intervals is always to check our conditions, so to make sure that it's okay to use whatever procedure it is that we want to use. So we have two things we always sort of need to make sure about here. The first one is, do I have a random sample? And then we'll ask something about how is my sample large enough, or is it normal? Okay, so first question, do I have a random sample here? Is it stated that I have a random sample in the problem? And if not, would you think that this is hopefully a representative sample anyway? So it's not stated, right? All it says is we have based on a sample. So we're not told anything about the sampling methods here. So what do you guys think? So just assume it's random. Why do you just want to assume it's random? or why might you be able to assume that it's a good random sample?
It was done for the environmental research journal,
Yeah.
so we're just going to assume that they wanted to get good data, so they would actually take a random sample, or else it would skew their data.
Yeah, that sounds great. So the response was, this is a study in a peer-reviewed research journal, and so we can assume that they wouldn't be trying to skew their results or something, and would have. We have to trust that they have good information here. So it's not stated that we have a random sample, but it's safe to assume because the study is reported in a scientific journal. Okay, so we're going to trust the peer review process, and hopefully that they've done their homework to make sure this is good information here. Okay, so that one's good to go. Put a check mark by that. The next thing I need to check is, well, we can think about, is the distribution normal, or is my sample size large enough? Again, if your sample size is bigger than 30, you're sort of good to go regardless, right? But here n equals 16 is, of course, less than 30. And are we told anything about the population distribution? So what's the distribution of the pulmonary compliance of these folks who have been exposed to asbestos? Not told anything, right? Doesn't say the distribution of pulmonary compliance is normal. Doesn't say anything like that. So in this case, what we need to do is we need to find a way to look at the data to kind of see if it looks like this information is at least somewhat close, or if this representative sample tells us that the distribution is something that's at least somewhat close to being normal. That's kind of what we need to do when we're not told. And so to do that, we're gonna jump over and look at JUMP and look at a statistical analysis thing which you can use to help you look at data and help us do some calculations here. So this is I'll say just another word about JUMP after I finish up this example. Okay, so what I can do is I can hop over here to JUMP, and here JMP or JUMP. Here I have a list of those 16 numbers. So on that slide that's right behind it there, I've entered those 16 numbers into a column here. And if I want to look at this information, I can go to the Analyze menu, click on Distribution, and drag my variable of interest over here. And I'll put up some instructions on how to do this. Click OK. Then I'm actually going to look at it this way. Okay, so here's some information that I can get out of JUMP without any problem at all, really. So on the left side here, I have a histogram of those numbers, and then on the other side, I have some summary information there. So the histogram is what I need to look at to say, is my data, does this data look like it might have come from a normal distribution? Is it close to looking like it came from a normal distribution? And it's kind of weird because it has those gaps in there, but if you kind of imagine the overall trend of this data, what do you guys think? Looks normal. Yeah, I mean, doesn't look exactly normal, and again, having those spaces in there makes it look kind of weird. I don't think I can draw on this now, but the point, I would say this is fine. It's not going to look exactly normal, but it's somewhat symmetric. It has most values kind of in the middle, and it's kind of less values on the edges. So while it's not perfectly normal, this is definitely good enough anyway for us to go ahead and make the calculations. So I'll go back and write that on the slides here again, but before we do that, just to point out that here, and you probably can't see that very well, but in the upper right corner there, I have the summary statistics of those 16 numbers. So I have the mean, I have the standard deviation, and I have a bunch of other information. But the two numbers that are important, I have the mean, which is x bar, and I have the standard deviation, which is s. So those are numbers that we will use to do some calculations here. So let's, yeah. Okay, so let's, keeping that picture in mind, so our sample size is not bigger than 30, but the histogram looks close enough. Histogram looks close enough to normal. So it's kind of the rare case that, again, we just need this thing to be somewhat close to normal. As long as, you know, like all the values weren't off to one side or the other, or there wasn't something really funky going on, you kind of just want to make sure that that's not happening here. Okay, so therefore, we're going to say it's not, n is not bigger than 30, but still we're okay with the form of the distribution here. Okay, so now I want to calculate, now that I'm sure that I can use this procedure, I want to go ahead and calculate this confidence interval. Let me just write down, so what I found from JUMP, I found that the sample mean X bar was 209.75, and I found that the standard deviation S was 24.156. and n equals 16. Okay, so the only thing yet I need is my critical value t, and I want a 95% confidence interval. So what does that mean alpha is if I have 95% confidence? Yeah, so alpha over 2 is 0.025, so alpha here is going to be 0.05, so, and then I have 16 minus 1 degrees of freedom. So I need to figure out what that critical value is. Yes, Kyle.
So we like look at the histogram to see that it was kind of normal, just to be able to use T. Like if it wasn't even close, then we would not be able to do anything like it.
Absolutely, yes. So the question was, so we looked at the histogram just to make sure that we were able to use this T interval. If it wasn't something close to normal, then yes, you would not want to use this confidence interval. So that was kind of our check to make sure that it's sort of okay. That yeah, to make sure that the procedure is going to give us something that's reasonable, or something that we can trust, some results that we can trust for that confidence interval. Yeah.
Like if you looked at the median and like the mean, so they were close to each other in that histogram with all the data you had, you also looked at like within 2 standard deviations, and if you looked at those as being close, would that be like confirmation if like it's really not, like if there's a lot of gaps like this, or even more, is that something you can use to confirm it? If it's approximately looks normal, but then use those.
Yeah. So the question was, so can you also look at, like, compare the mean and the median, or look at sort of within 2 standard deviations, do we have most of our data, that kind of a thing? Yeah, that's another good way to sort of check. So here you can see the median is 207. That's pretty close to the mean, which means that we have something that's something we're not talking about. But when the mean is about the same as the median, then you have something that's pretty symmetric. Yeah, if I go, so the mean is 209. If I go plus or minus 2 standard deviations, it's plus or minus 50. Actually, yeah, that's really close too. All my information is within that. I guess so. Yeah, so those are all good ways also to think about this. The interesting thing is that when your sample size is this small, so maybe I'll do this next time. Maybe I'll do this next time. But if I take, there's a way to generate numbers that I know are from a normal distribution. You can use that, do that using statistical software like this too. So if I take 16 numbers that I know are from a normal distribution and make a histogram of them, the histogram can look pretty weird because it's just sort of the variability that you get in sampling. So if I take a lot more numbers, then I will get something that looks a lot closer to normal. But when your sample size is small, the histogram can look kind of funky, even if you have something that is really from a normal distribution. So really, again, I guess the bottom line here is it's just, is it close enough? Is it something that's sort of symmetric and doesn't look too crazy? So it's not like I have all my numbers off. It's not like I have something bimodal going on where there's sort of two large peak values in that histogram or something like that. But yeah, then it is just a way to confirm, is it okay for me to use this procedure? Yeah. Great questions. Okay, so let's remember we need to find this critical value. So to do that, we can jump over to our friendly table here. I want, again, n minus 1. N minus 1 is 15, so I want to come over here and look at the 15 row. And then I want 0.05 divided by 2, so I want 0.025. I want that column. So I can go into that column and trace over here to find 2.131. So my critical value here is 2.131. I know the chart. So, so the chart lists they have an alpha here, but again they're saying the shaded area above is alpha. So we want that shaded area above to be alpha over 2 when you have a two-sided interval like this. So yes, just be careful about that. Okay, so then my confidence interval is x bar plus or minus t 0.025, 15 times the standard deviation over the square root of n. Well, we have all this information, right? X bar is 209.75 plus or minus 2.131 times 24.156 over the square root of 16. And that will give me an interval here of 196.88 and 222.62. Okay, so not quite done yet, right? We need to interpret this thing yet. So we'll just say, what we can say here now is that we are 95% confident that the true average pulmonary compliance for workers exposed to asbestos is between these two numbers, 196.88 and 222.62. So again, we're 95% confident that the true average pulmonary compliance for workers exposed to asbestos is between 196.88 and 222.62. What units were those in? That was in... Yeah. So now you need to go to a doctor, or maybe if you guys know more about this, you could tell them what these results are and they could tell you is that, I'm assuming that's probably a bad pulmonary compliance. So that's where my expertise as a statistician ends, and you go back to your collaborator and tell them your results, and they can interpret those for you. Okay, so that's a little bit more of a sort of a full walk through this. If you have a data set, it's kind of how to get this thing. One other thing that I did want to show you about JUMP here is this is again kind of hard to see, but if you look under the summary statistics, you see in the top right there, you see mean, standard deviation, standard error, mean, and then you see upper 95% mean and lower 95% mean. Well, those numbers look a lot like what we just calculated, right? 196.88 and 222.62. So there you go. JUMP will even do the confidence interval for you if you put if you have the data in here to get input like that. It's another reason to use statistical software. It makes your life even easier. So that's again, you have to have the list of numbers to do it this way, but that's sort of what you'll have in real life, presumably. So as far as So I'm not, the homework assignment for this week does not require you to use jump. In fact, I don't think you can, because I've just given you the summary information, X bar and S, instead of the actual list of numbers. It is about time to maybe start going about getting jump on your computer. I think that's something for us to start getting familiar with. On Carmen, I did post a little help guide on how to install jump on your computer. There's a website you can go to. It's free for you guys as OSU students. And you can download it from or you get an email with a link to download it if you sign up for it. And there's some instructions there on how to actually do that. So take a look at that. Let me know if you have any issues doing so. There's a few issues with getting like a license key or something. It's a little tricky, but let me know if you have any questions. So there's a document about that up on Carmen on the content page. Okay, other questions or comments before we move on? Okay. So that's all we're going to say about in here about confidence intervals for now, although I think we have a good understanding. Most of the confidence intervals you will see anyway, are of one of these types. Okay, so moving on here to Chapter 8, which we're looking at, talking about hypothesis testing, which is sort of the other, it's very closely related to confidence intervals, sort of another of the main forms of inference that we'll be doing here in this class. So sort of as a motivating example here, we can go back to our paper manufacturing example. We'll change it slightly here. But again, remember this manufacturing process, they want the holes in their paper to be punched 8 millimeters from the edge of the paper. But again, due to vibrations or variability in the manufacturing process, they're not always exactly 8 millimeters, of course. So we didn't say this before, but now let's say, well, we know that the distance that the hole is punched from the edge of the paper varies according to a normal distribution with standard deviation 1 millimeter. So here this is my population standard deviation sigma. I'm told that about the distribution of the numbers here. Okay, so you can imagine that you maybe work for this company and they want to know if their machine is adjusted to the correct distance. And so what we do is we take a sample. We sample 25 sheets of paper from this process and measure the distance from the edge of the paper to the hole here. Okay, so I take a random sample of 25 sheets of paper, I measure the distance, and I find that the sample mean here is 8.0282 millimeters. And so again, bottom line is the company needs to make a decision. So maybe they're asking you to help make this decision as to whether or not I need to call somebody to come help fix this thing for me. And this is maybe this is a very expensive thing to do. I don't want to do this if I don't have to. So the question I need to answer is, are the hole punches on average, are they 8 millimeters from the edge of the paper? So either yes, the holes are 8 millimeters from the edge of the paper, and I don't need to call the engineer, or no, I do need to call the engineer. So no, the process, the settings are somehow messed up here, and I need to call the engineer. So how can I answer this decision? Any thoughts? Without looking ahead too far in your notes? Yeah, Kyle.
Take a confidence interval.
Yeah. That's excellent. So we could calculate a confidence interval, right? So I could calculate using X bar. I could calculate a confidence interval for mu, which is the sort of the true average distance from the edge of the paper. And again, how could I use that confidence interval? I think you said it, but say it again.
The mu that they say is the real mean isn't in there, then it's probably not the right mean.
Yeah. So if I want to see something about if the mean that I'm saying or the mean that I want is not in that confidence interval, that is a red flag that maybe I do need to call this engineer. So if the number 8 doesn't fall in my confidence interval, then you could think maybe I need to call this engineer. So that's an excellent response. That's exactly right. So that's to make the decision. That's one great way of doing it. So we can calculate a confidence interval and see if 8 is within that range of reasonable values. The other way to answer this question or make this decision is to do something called a hypothesis test, and decide directly whether this is sort of a reasonable value for the mean. The reason, so you might say, so why then are we even talking about hypothesis tests if confidence intervals will do the same job? And that's a valid point. I think in some classes they only teach one or the other of these things. I guess what I would say here is that for my confidence interval, this depends. So let's say whether 8 millimeters is in the interval depends on the confidence level. Right? So what if I do a 90% confidence interval and 8 is not in that confidence interval, but then I do a 95% confidence interval and 8 all of a sudden is in that interval. So there's maybe, you can think about, there's maybe some subjectivity going on here with how the confidence level that you choose, and so that maybe doesn't seem very satisfying. So that's maybe my argument for also talking about this other thing called hypothesis testing. So as an example, this is kind of the type of question that hypothesis testing can help us answer. So is the true mean here of my manufacturing process, the true average distance, is that 8 millimeters? Is that true, or is it broken and needs to be fixed? Okay, so let's discuss some details, kind of thinking about sort of my steps here for a hypothesis test. And this is kind of like how science works in general, right? We think about sort of the question that we want to answer. We maybe collect some data, we perform our test procedures, and then we make a decision. So this is kind of, you guys as scientists, I think you might connect well with kind of this logic. So specifically in this class, sort of our main steps, we want to define what parameter that we're interested in looking at. So before it was the sort of the true average distance from the edge of the page. We want to determine what our hypotheses are, so we'll say more on that. We will observe a random sample, so we'll observe some data. And then we'll, very clear here, we'll perform the test procedures and make a conclusion. So I think we're already pretty comfortable with 1 and 3, kind of thinking about what parameter we want to estimate. It's going to be a population mean or a population proportion, those kind of things. We already sort of have an idea about observing data, taking a random sample, but we do need to say something about these other few sections. So how do we go about determining the hypotheses here? Okay, so first of all, maybe what are hypotheses? So the definition that we'll use in here is that in statistics, a statistical hypothesis is a claim or assertion about the properties of a population. So it's going to involve the properties of the population. By that I mean the parameters of a population. Or it could even be the form of the distribution. So that says parameters. So when we're formulating hypotheses, again we're making a claim or assertion about something about the population, be that the parameters of that population or sort of what distribution does that population look like. And so in this class we'll talk more about that first one, making claims about the parameters of a population, and the other ones we'll leave for your future statistics courses. Okay, so for example, what are some examples of these things? So if my question is something about how far from the edge of the paper are these holes drilled, possible hypotheses would be, if I'm thinking about the population mean, maybe I'm saying that mean is 8 millimeters, or you could also say it's It's not 8, but it's 7 millimeters. I could also include sort of inequality statements here. So I'm saying it's not equal to 8 millimeters, or maybe it's greater than. So these are all examples of hypotheses. And maybe more specifically, what this first one says, for example, is that mu equals 8 millimeters. So what I'm saying is that the population mean is 8 millimeters. Yeah.
It's like within a range. Like, is that possible?
So could you say it's within a range? Absolutely, you could. So you could say something like, well, that's maybe this one down here, right? Mu is greater than 8. I'm guessing probably what you meant is like mu is between 7 and 9 or something like that. Yeah, so you could also say maybe mu is between 7 and 9, something like that. That's a statement about the population parameter, right? So that could be a very fine hypothesis. We won't, for this class anyway, we'll do more. We probably won't be able to answer hypothesis questions like that. It'll be more like mu is greater than 8, or mu is less than or equal to 7, or something like that. But you absolutely could do it that way if you wanted to as well. Okay, so just write down these other ones. This one is saying mu is equal to 7. Mu is not equal to 8. So I'm just making a claim or an assertion about something about my population. Here we're talking about the population mean. Okay. So let's take this one step further. There are two specific types of hypotheses that we'll talk about in this class. First one is called the null hypothesis. The second one is called the alternative hypothesis. And this is kind of the two things that we're deciding between when we're answering a question like we did earlier. Okay, so the null hypothesis, which we'll denote with a capital H and put a 0 in the subscript there. That's the claim that we're sort of initially assuming to be true. And then the alternative hypothesis, on the other hand, denoted H with a A in the subscript, is sort of the opposite of the null hypothesis. So this is it's contradictory to, or it's opposite of H0. And I don't know if you've taken statistics classes other places, you might have seen that called H1, H sub 1. We'll use H sub A in this class, but that's something you may be seeing there as well. Okay, so null hypothesis is kind of what you're assuming to be true initially. The alternative hypothesis is the opposite, pretty much, of whatever claim you've made to start with. And so we can say one more thing here. Let's say, so in general, typically, the null hypothesis is sort of the status quo. And then the alternative hypothesis is usually is what you're hoping to show is true. So it's what you want to show to be true. And that one maybe we'll formulate the hypotheses of our hole punching example here in a minute, and that might make that clear, a little more clear. So the null hypothesis is sort of the status quo, or that sort of nothing is happening here, and the alternative hypothesis is what we want to show. So maybe whatever that might be, there's usually a goal that you have, or the question that you're asking usually has a direction that it wants to go one way or the other, and that's what you put in the alternative hypothesis. Okay.
Could you explain that again one more time?
Yes, absolutely. So null hypothesis, let me say, this is saying there's sort of nothing, there's nothing interesting happening or just that sort of Let me hold off on that question until we do. I'll formulate the hypotheses in terms of that hole punching example. I think that'll make a little more sense. I think it's maybe easier to think about, maybe ignore that, but think about the alternative hypothesis is usually what you're hoping to show. So in that previous example, I may be interested in knowing, is my manufacturing process broken? So that's what I would put in the alternative hypothesis, that the true average distance from the edge of the paper is not really 8 millimeters. And maybe in a different setting, it's a little bit more clear about what you're trying to show. Like, for example, if you're testing a new drug, for example, for a pharmaceutical company, your null hypothesis would be that drug doesn't help at all, right? It's sort of just you might as well just take a sugar pill or something. Whereas the alternative hypothesis would say, no, this thing actually really is making people better in some way. So that's kind of what I'm hoping to show with a new drug. I want that thing to be successful, of course. So my alternative hypothesis would say, yes, the drug is actually helpful in treating whatever condition I'm looking at. Does that make a little more sense?
Yes.
Okay.
We'll see how they relate to each other.
Yes, absolutely. We'll say I'm not done talking about this yet. Yeah. Yeah. Okay, so again, there are more general cases here, but for this class, the null hypothesis will always be of the form that theta is equal to theta 0. So this is theta naught. And this is just my the hypothesized value for the parameter theta. So I'm always going to say my null hypothesis is always going to be that whatever parameter I'm interested in here is equal to some value. So population mean is equal to 8, for example. And then we'll have three possibilities for what the alternative hypothesis looks like. Instead of being equal to theta 0, maybe we're interested in seeing if it's less than that value. Maybe we're interested in seeing if it's larger than that value, or simply if it's not equal to. So these have a special name. These are called one-sided tests. And this down here is called a two-sided test. So our null is always going to be the parameter is equal to something. The alternative will be, am I saying that that parameter is less than that value, greater than, or it could be a not equal to in there as well. Okay, so let's go ahead and say this for our paper hole punching example. So again, here again, mu is the average distance from the edge of the paper. And so I'm going to have my two hypotheses. I'm going to have my null hypothesis versus my alternative hypothesis. And they're both involving this mean parameter mu. Okay, so sort of the question I was originally asking, what did that say? Are the hole punches on average 8 millimeters from the edge of the paper? So I want to know if the issue will be if the process is broken. So I want to know if the mean is actually something not equal to 8. So over here, my alternative hypothesis, I'll say the mean is not equal to 8. But we'll start with the idea that mu is actually equal to 8. So here, this is sort of like my mu 0. Or that's my hypothesized value for the population mean mu. Okay, so I'm not interested in knowing is the hole punched more than 8 millimeters from the edge of the paper or less than 8 millimeters. I just want to know if it's different from 8, if it's somehow not equal to 8 there. Okay, maybe one more example here. Practice writing our hypotheses. So USA Today reports that 5% of American adults claim to have seen a UFO. Anybody in here seen a UFO? Oh, did you ever? Okay. Haven't seen a UFO? Okay.
Yeah, sorry.
That's fine.
So we just wrote our hypothesis.
Yeah. Exactly right. So we're just writing out what our hypotheses are. We haven't actually made our decision yet. We haven't actually said, yes, I need to call an engineer, or no, I don't need to call an engineer. We're still getting there. Yeah. Good question. Though. That's exactly where we're going. So in general, that's where we'll go right after this. Okay. Anyway, about UFOs. Has anybody in here seen a UFO? I didn't mean to laugh that off if it was. So we suspect that this percentage is probably an overestimate of that true percentage, and we want to test this claim. So let's get some notation. Let's let P equal the population proportion of Americans who have seen a UFO. So we can test some hypotheses about this. We're both going to involve this parameter P. The null hypothesis is always that P is equal to something. So again, what I'm suspecting here is that the percentage of 5% is actually an overestimate of this true population proportion. So what should my alternative hypothesis be? It's going to be P and then something 0.05. And what inequality symbol do I want to put in there? I think I heard less than, right? So I want to know if this population proportion is actually less than 0.05, and sort of the opposite of that, or we'll start with the claim. We'll assume that what we've been told is true. So that's kind of another way to think about the null hypothesis. So we can assume that we've been told the truth. Yeah.
I was going to ask the same thing. Like, would you have to do equals, or would you?
All right. So yeah, technically an opposite would be something like this, right? That's a great question, and I have somewhere in my notes. I know I have a comment to say that is that is an issue. So great question. So yeah, so the response is P equals to 0.05 and P less than 0.05. Those aren't really opposites. What about all the values of P that are bigger than 0.05? Again, you could kind of test. You could absolutely set the hypotheses up that way, but sort of for the purpose of this class, we'll go with this. So again, kind of the way to think about that is if the proportion P is really bigger than 0.05, that's sort of telling us, that's sort of the opposite of the question we want to know anyway, right? So if the proportion really is 0.08 or something like that, I still know that what I'm assuming is not true. So I'm still seeing that the percentage is not actually less than 0.05.
So it's dependent on how we feel the right answer should be, right?
As far as the alternative hypothesis goes, yes, definitely. Yeah, that again, the alternative hypothesis says kind of the claim that you want to test. So I want to know if the population proportion is less than 0.05. So I'll put that in the alternative hypothesis. Yeah.
So like the null hypothesis really isn't that important. It's your alternative because that's what you're trying to prove.
Exactly right. So the null hypothesis comment was null hypothesis is not really that important. It's more, we're more interested in the alternative. That is true. I mean, it is good to make sure that you set up the null hypothesis, but yeah, you're usually more interested in what's happening with the alternative hypothesis. Yeah. Good questions. Okay. So that's how we can set up our hypotheses. So I think I wanted to put this, well, we'll talk about this first. Okay, so those are my two hypotheses. I have my null hypothesis and my alternative hypothesis. So then what are my possible conclusions? So what I can, again, once we'll talk about how to do these test procedures, probably do that on Wednesday. But the eventual decision that I will make is one of two things. So either one I will reject, either I'll reject the null hypothesis, which means that I would sort of go with what the alternative says. That's kind of what I'm hoping to show. Or I will not reject the null hypothesis. So the other option is that I will fail to reject the null hypothesis. Yes, sir.
So in the last example, we could reject and fail to reject and still not prove that HA was correct.
So we could say that again? We could reject.
We had P equals 0.05,
Yeah.
right? And we could
Yeah.
say that that's not true, and let's say 0.08, but the assumption was also not true.
That's right.
So we
Exactly.
seem to fail in both categories.
Yeah. So that's a great question. So the response was, so if I couldn't you be sort of rejecting both of these things? Like the proportion is not less than 0.05, but it's also not equal to 0.05. I see what you're saying there, and that's kind of where you see an equal sign in the null hypothesis, but think about it being a greater than or equal to. So you're really trying to say something about your alternative hypothesis. Is that true or false? And realizing that if P is really bigger than 0.05, that's sort of refuting the claim the idea that I had anyway. Yeah. So the reason for this sort of funky language. So I have reject the null hypothesis versus fail to reject. I'm not saying. Note that this is not saying. I'm not accepting the null hypothesis, right? I'm not like proving that the null hypothesis is true. I'm just saying that it's not true. And this is maybe this feels a little bit weird, but I would think about a legal example. If you're on a jury and you're listening to a trial, at the end of the story, the defendant is what's the end result of a trial? Yeah, right. They're guilty or not guilty. The defendant is never declared innocent, right? That's kind of the same idea that we have going on here. We're either saying that the null hypothesis is false, so that's like a guilty, or we're failing to reject. So we're not saying that the person is innocent. We're just saying that they're not guilty. That's sort of the like the scientific process here, right? I can't ever prove that something is true, especially not in this setting. So that's the reason for that.
Evidence, or
What's that?
is it because we don't have enough evidence to say that it's another word instead of not guilty or
Yeah.
innocent?
Right. So the response was, is that because we don't have enough evidence or something like that? Well, that's exactly the intuition, right? And I think that's what happens in a trial too, right? Someone is declared not guilty, but if there were more evidence, then maybe they would have been declared guilty, right? So it's kind of that idea that we're looking at the evidence that we have, which is the data that we've collected to help us make this decision. Maybe that data is not complete, and if I had more data, maybe I'd make a different decision. But again, you have to use the information that you have.
Is there a comment from, like, in the first time why we chose to do this, like, to say that it's less than 0.5, because we have a strong intuition that it could be that, right?
Yes,
Probably
right.
That 5% of Americans watch that.
Yes, exactly. So right. So we're using the intuition that we have to set up our hypotheses, and then we'll use the data that we collect to help us answer that question. Yeah. All right. Hey, great discussion, guys. Thank you so much for being here. We'll pick this up on Wednesday. Have a good rest of the day.